Design of RF up-down converter for signals using GNU Radio and SDRs.
Imagine a world where wireless communication is faster, stronger, and more efficient. That's the revolutionary impact of RF up-down conversion. This technology is a cornerstone in the tech world, significantly enhancing wireless communication. The magic behind improved wireless communication lies in the RF up-down conversion. Software-defined radio, SDR, is a technology that allows the implementation of radio communication systems in software. This is in contrast to traditional radios, which use hardware components to implement the different functions of a radio system.
GNU Radio is a free and open-source software development toolkit that supports the development of SDR applications.
It provides a wide range of signal processing blocks that can be used to implement different radio functions, such as modulation, demodulation, filtering, and equalization.
SDRs are hardware devices that can be used to transmit and receive radio signals. They are typically much less expensive than traditional radios, and they offer a greater degree of flexibility. Our project design is for an RF up-down converter that can be used to convert radio signals from one frequency band to another. This can be useful for a variety of applications, such as 1. Building a custom receiver for a specific frequency band. 2. Extending the range of an existing radio system. 3. Translating signals between different frequency bands. We are using GNU Radio to implement the up-down conversion process. The SDR is used to transmit and receive the radio signals. We are still under development, but we are excited about the potential for our project to be used to build new and innovative radio systems. In the next 2 minutes, we will provide a more detailed overview of our project design, including the following. 1. The different signal processing blocks that we use in our design. 2. How we use GNU Radio to implement the up-down conversion process. 3. The potential applications for project.
For uplink conversion, first we are taking the sample rate, which is the number of digital samples taken per second to represent an analog signal for processing as 60 gigahertz. And then we take two signal sources, one operating as signal source and other as local oscillator. Then we change the output type of signal source as float and change the frequency to 1 gigahertz. Then we change the output type of local oscillator to float as well and change its frequency to 100 megahertz. Now we bring a multiply which works a multiplexer and make it float output as well. And now we connect the ports and bring a frequency C which displays the output. The center frequency is kept 0 while the bandwidth is 60 gigahertz. Now we connect with the multiplier and run it. We see a signal of 1 gigahertz. Then we take another signal source and make the output float and change the frequency to 6 gigahertz. and bring another multiply and connect the ports from the previous multiplier and this signal source. The result generated becomes the RF frequency, which we display using another frequency sync. Keeping the center frequency of the frequency sync as -1 GHz and the bandwidth 60 GHz. Then we pass it through a high-pass filter with a cut-off frequency of 5.9 GHz and the transition width of 50 MHz. The result is then passed on to a frequency sync. With center frequency -1 GHz and 60 GHz. Which finally gives us our desired output in 6 GHz, which is C-band. For down conversion, we change the sample rate to 300 GHz and take two signal sources. One operating as signal source and other as low oscillating source. We change output type of signal source to float and change the frequency of to 6 GHz. While we change the output type of low oscillating source to float and change the frequency to 400 MHz. Now we take a multiplier and change its output type to float and connect the ports from two signal sources. Now we take a frequency sync and change its output type to float and change the center frequency to 1 GHz and connect with the multiplier to display the generated signal. We see that peak value of generated signal is 7 GHz, which is in the C-band range. Now we take another signal source and change the output type to float and change the frequency to 7 GHz. Now we bring another multiplier and change its output type to float and connect its ports from the previous multiplier and signal source. The resultant signal generated is the RF signal. To display it, we use another frequency sync. We change its output type to float and change the center frequency to 1 GHz. Finally, we pass it through a low-pass filter. We change its output type to float and change cutoff frequency to 3 GHz and transition width to 50 MHz and connect with the output of multiplier. We then display the generated signal using a frequency sync by changing its output to float and center frequency to 1 GHz. As we can see, the generated signal has its peak value at 1.2 GHz, which is in L-band range.